I'm going to discuss homology the way I learned it when I was a graduate student at Princeton, in sort of intuitive geometric terms, and then discuss a new algebraic structure in a particular class of spaces, which we might call space of strings or certain kind of loop spaces. But that is very natural from this elementary graduate student description of homology. And this is joint work with Moira Chass. And first, there's a little bit of philosophy here at the beginning. So the idea is that we're going to use the method of algebraic topology to treat spaces, and finite dimensional and infinite dimensional spaces are treated on an equal footing by considering, I hate having notes, by considering, well, so the two examples are like a finite dimensional manifold MD, and that's a finite dimensional example, and then all maps, say smooth or continuous, the details are rather going to be unimportant, of the, say, the circle into the manifold. And the way you treat these spaces, you break them into blocks or cells, which you take to be generators of a vector space. You can grade the vector space by the dimension of the cell. Then there's a natural boundary operator on this space made up of the linear combinations of the boundaries of the blocks. And the idea which I'd like to emphasize is that this has both a geometric and an algebraic flavor at the same time. So you can kind of move between the two domains. So, on to my next slide. So for example, take two cycles in a manifold. I had a more elaborate picture before, but take two cycles in a manifold. These are linear combinations of blocks where the faces cancel in this vector space. The boundary operator is 0. And you can imagine that they're in general position, and you look at the intersection. I have a better drawing on the previous slide. These are like two cycles, two one-cycles on a surface. So the surface I didn't draw, and they're intersected transversely. For example, this goes around the back of the surface, so it doesn't have to cross here. This is not in the plane. And then at each intersection point, you can assign an orientation, and you get, in this case, the product of the two one-cycles is a 0 cycle. And, whoops, well, it doesn't matter. Geometry is invariant under rotation. So, actually, there's a second way to use this construction. If M has boundary, like if these are like pieces of the boundary of M, these four things here, you can take relative cycles, cycles whose boundary are in the boundary, and you can intersect them, and you get a product. Actually, you know, in general, you'll get an the cycle will also have a term in the boundary. Like if you intersect something like this and something like this, the intersection will run over to the boundary. And the relative cycles also form an algebra. And this is an explanation in the level of cycles why something called cohomology has a product structure for all spaces. Because every space, even with singularities, can be thickened up, at least in finite parts of it, can be thickened up to be a manifold with boundary. And then these relative cycles can be intersected, and you get a product. And you also have a third way is you have a duality. You can intersect interior cycles with relative cycles. So relative cycles and interior cycles are in a duality. Anyway, so just this same idea can be used in a number of ways to establish some of the early homological structures. Okay. Not so good at this. Now there's a second example, which is rather different, of where the cycles, homology cycles of a space, have an algebra structure. This is an associative non-commutative. The other one, I said it, but I mean it was there. This previous intersection product in cycles gives a graded commutative algebra structure on the homology of a manifold. It's graded commutative algebra. Now this one is a different thing. Suppose you have, this is in the space of mappings of the circle into M, which start and stop at the same point. So here we have, here's the point here, and here's one cycle that goes around and stops here, X, and here's another cycle that goes around and stops here. And now maybe you have a cycle of these. Remember, you have a cell you have these cells in this function space, and then groups of cells that make cycles in the function space. And now you can call one of these cycles X. I've just drawn a typical element of the cycle X in the function space of maps that start and stop at a given point. Y is a typical element in the cycle Y of maps that start and stop at the same point. And then you can take any point in the parameter space of X and parameter space for Y. And so for each element in the Cartesian product, you can form the cycle that goes around first the X cycle and then around the Y cycle. And so you get a product on cycles. So I've used X and Y twice, but this is X here means a family of cycles, a family of circles that form a cycle in the base loop space. So this is a specific case of the idea that if you have two cycles in a group, you can multiply them to get a cycle in the group. The dimensions add. In the previous discussion, when we did intersection of cycles in MD, it was the codimensions that added. Because when you intersect, it's the codimensions that add. And here the dimensions of the cycles add. So these are not at all the same construction.
Are these mappings from S1 to M, or families of mappings?
Families of mappings of S1 to M. The space, so I gave the example, I'm considering spaces divided into cells applying homology. So the objects I'm discussing are cycles and spaces. So I'm taking the space now to be the base mappings of circles into M, so-called base loop space. So if you have a cycle of base mappings and another cycle of base mappings, you can form the Cartesian product cycle. You take a point in the Cartesian product, and you go around the first cycle, then around the second cycle. So it's just I forgot the name, Pontryagin product maybe, anyway, forget names. This is the definition. Okay, so in other words, if you consider the homology of all spaces, I mean, just consider the homology. These are vector spaces, the kernel of the boundary operator mod the image. And I've given two examples where the homology groups form a graded, has a graded algebraic structure. I also, for purposes of completeness, did this relative thing, which, so to speak, encompasses the familiar notion that the cohomology always forms an algebra for any space. But I'd like to kind of forget that now. I'm talking about homology. So in general, the homology of a space does not form an algebra. I've given two examples where it forms an algebra. First, the homology of a manifold, intersection theory. Second, the homology of a group. But I didn't want to do the general group. I want to do something which is not a specific thing, which is almost like a group. The space of based maps, circuits in a space that go around and come back to a given point. The space of all such circuits, it's a huge space. Cycles in that space can be multiplied, and you have an algebra structure. So these are classical algebraic structures. So, any questions? I mean, explaining it kind of strangely, maybe. Huh? What? What's the boundary? What's the boundary of what? 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 Oh. Any space can be divided into cells. These cells have boundary, and you can make homology. I'm talking about the homology of any space. And now I'm saying take the space to be the space of mappings of a circle into, I'm always working with M because I like M, which start and stop at the same point. In other words, maps of the circle that take a given point into a base point. Then the homology of this space of mappings forms an algebra. Okay, you have to sort of take manifold, take mappings, take cycles, and form an algebra. It's just take a cycle and take any 2 points. You get 2 loops at the base point, go around one and then around the other. Okay, it's okay. Now we get to the first main okay, yeah, let me, no, I'm going to say something else first. It's a little too sophisticated, maybe. But both of these operations, namely intersection of cycles in a manifold or the multiplication of cycles in the based loop space, are defined on the chain level. You can actually perform these operations on the chain level. You don't have to have, it's not just for homology. You can actually have it for things with boundary. They respect the boundary in the sense that when you intersect 2 sheets with boundary, the boundary of the intersection is, the usual formula. And the boundary of this product, I said, because it's like the Cartesian product, the boundary of a product is the obvious formula too. So these product structures go to the chain level, or really are at the chain level, and they respect the boundary operator. The Leibniz rule is true. And that's why they pass to homology. And these operations satisfy their identities that I mentioned. I mentioned that the intersection product was commutative and associative. And this loop product is associative. Now, literally speaking, these, on the chain level, they're not literally associative because, like, when you go around one loop and around the other, you sort of use the first half of the time interval to go around one and then around the other. And then when you do 3 things, you use a fourth and a fourth and a half. So up to some fudging, they're associative. But there's a rather, and the, what? Oh. Oh, up to infinite homotopy. Oh. Right. Homotopy. So these things, these identities I mentioned at the level of homology are strictly true. Namely, the homology intersection product is commutative and associative. The loop product is associative, but not commutative. These are true exactly on homology. But at the chain level, they're morally exactly true. They're not literally true at the chain level. However, the discrepancy is sort of in a contractible set. And there's a sophisticated notion now in algebraic topology, which has been elegantly understood in recent times and very easy to prove in these cases, explaining what this notion of infinite homotopy is. And it's easy to prove in these cases using this contractible choices idea. All the errors are like in intersection theory, when you move things to be transversal, they're local deformations. And a space is locally contractible. So all the little errors can be built into chain homotopy. So the whole sort of strength of this approach, in my mind, is this idea of this boundary operator and the fact that you can correct identities at the geometric level that you would like to be true at the algebraic level using this boundary operator with little homotopies. And if you have a derived calculation where you use these identities many times, the homotopies will sort of build up in it. But like if you prove things 2 ways, you'll use manipulations to get around 2 things. There'll be a loop of homotopies. You can also fill in that loop, and you can fill in the fill-ins and so on. So there's this sophisticated notion of what identities at the chain level mean up to infinite homotopy, and one can keep track of this. So, and when you write things in the correct, elegant, recently understood way, they are just as if they are exactly true. Like when you write things out with these free algebras of Kontsevich was talking about, for example. But anyway, I want to illustrate. So now we get to this. Now we get to the first main construction. Let's consider now a new loop space. This is the space of all loops in M, all maps of the circle in M. They don't start and stop at the same point. They start and stop at any point. Now take two cycles in this space. So here's a cycle of loops, a green one, and here's a black one in the loop space. And now we want to combine the two previous ideas to define an algebraic structure, an algebra structure in the homology of this space. And this is the new point. Okay, it's happening right now. This is the point. Okay, and it's very easy. But we combine the two previous steps. We want to multiply these loops, but we can't multiply a loop over here and a loop over here, so we just do the first thing, which is we use the previous two ideas. So first we multiply the two cycles of loops. We multiply the cycles of the moving base points. See, we have this moving family of loops and a moving base point. So this is the moving base point of one family and the moving base point of the other family. So we first intersect those in the manifold. And actually, these could be trillion-dimensional cycles, and the manifold could be four-dimensional. We still intersect them. You just look at the map into the product, make it transversal to the diagonal, take the pre-image. That's what intersecting means. And now we get, along the intersection, the green loop. At any point of the intersection, the loop in the green family and the corresponding loop in the black family have the same base point. So now we can multiply them. So we use the second idea. So we just use the two ideas together. So this, on the level of chains, defines a natural algebra structure on the free loop space of a manifold. Not of any space, of a manifold. So the free loop space of a manifold, the chains on it has a natural algebra structure. And this is it. You just use the two previous discussions. And this will take an I chain and a J chain and map it to an I plus J minus D chain, because you lose D dimensions by imposing the condition that the base point here equals the base point here. Those are D conditions, D equations in the manifold. So now the rest of the talk will be about discussing what are the algebraic properties of this operation. And then at the end, maybe some remark about a large family of operations to which it belongs.
What were I and J's? The relative dimensions?
Like the dimensions of the I cycle and a J cycle gives an I plus J minus D cycle.
Are they cycles? That's the dimension in the space.
Yeah, so they could be like a trillion. So a trillion and a trillion in a four manifold is 2 trillion minus 4.
What about this one coming from the circle?
Huh? No, because base loops, I was intersecting the base points.
No, but I and J include this one from the circle.
No. I is the cycle as a cycle in the free loop space. Yeah, right. Later we're going to use that one.
Just the base one have the same dimension.
What? Sorry? Look, this is copied. Don't write any sentences down. Just draw this picture in your notes. This is it. Huh? Well, you can work out what it. So intersect the I cycle and the J cycle, and you get an I plus J minus D cycle. And at these points, you multiply the loops. Yeah.
I and J is D all one in this picture?
Huh? Yeah, I and J are 1, yeah. And you're kind of in a surface. So you get a 0-dimensional cycle, yeah. Okay? What?
So I and J are always less than D?
No, I and J are not always less than D. I just explained that. If you want to intersect a trillion cycle, a trillion family, and a trillion family, and a four-dimensional family, you take the map into the map of the Cartesian product into M cross M, and you pull back the diagonal. Be brave. These are just the same operations we learned in graduate school. Okay. But, well, we can slow down at this point. This is really my main point. I'm now going to just start calculating, you might say. So we just combine the two known ideas of algebraic structures on cycles, and we get one on the cycles of the free loop space. It's so clear to me now that I have trouble saying any more about it. But I can understand.
Well, that's what was quite good.
Huh?
Like preparation. You have to say something.
What?
You have to say something. You don't stop here then.
Yeah, okay. Now let's discuss it, because it's interesting. A little thing happens now. So notice this is kind of an extension of the homology intersection of the manifold to the loops, because you can think of the points of the manifold as being just tiny little loops that are concentrated. So you see, in fact, the picture I drew, imagine these were like real tiny little loops. Then your remark about the cycles being less than d is relevant. Then when they intersect, I just get the product of tiny loops as a tiny little loop. So this is really just the ordinary intersection. So the sub part of this discussion, which is the previous first example. So this is kind of an extension of good old intersection theory to this huge space. That's good. All right. So we've extended the M example because tiny loops, the cycles of tiny loops in the loop space really are just homotopy equivalent to the constant loops, which are, that's really the manifold. Now this operation on the chain level is associative up to infinite homotopy because it just combines the two previous discussions of being associative up to infinite homotopy, and becomes commutative when we pass to homology. It also respects the boundary operator, and we can pass to homology. But it is not infinitely homotopy commutative, as we shall see. First, it's kind of interesting that it is commutative when you pass to homology.
Is what grading? What is the grading? Yes, we expect that, yeah?
Yeah, it's I plus j minus d. We're going to find out. What does it mean, infinite homotopy commutative? I kind of talked about that before. Okay, so there's another binary operation, which we'll call, on the chains of the loop space, which we'll call star, and there's a picture of it. Now, this goes up one dimension more than the previous dimension, because now you're going to allow x, the base point of x, to hit anywhere along y. So this will have one more dimension. Okay, so that'll have one I plus j minus d plus 1. Okay, because the equation has one more degree of freedom in it. X star y. This is a non-associative binary product. In fact, it has, where's Victor? It has the same, where is Victor?
Yeah.
Victor. It has the same properties as your normally ordered product. I mean, you showed me this morning. Yeah. And this, it's sort of clear from the picture that this thing will not commute with the boundary because there's kind of a singularity at this other base point. But if you sort of slide this point around to here and do things in the order, see, x times y means you first you go around, I don't have the directions on here. This is another operation. You go around to here, and then you go around to here, and then you go around to here. That's the operation, x star y. The base point is over here. I didn't explain that very well. Now, see, as you slide the loop x around to here, it's like y times x. If you slide the loop around to here, it's x times y. So the commutator with the boundary applied to two elements is, I mean, the way it doesn't commute with the boundary, this operation, is just AB minus BA. And I was careful to write the signs in this time, and it's sort of obvious from the picture. Sliding around it. So here's a natural, so this is the chain homotopy showing that in homology, it's going to be commutative. So this defines a graded commutative and associative graded commutative structure on homology. What? What means what? This is like XY. I mean, I think of this as a binary operation, and I want to compute the way in which it doesn't, I want to compute the way in which it anti-commutes with the boundary operator. So that's like the deviation of this from being a derivation for boundary. That's what the commutator means. And that deviation is this.
How does D act on the shared AB as well? Yeah, so you
The way it acts on a product.
Oh, so DA times B.
Yeah, yeah.
DA times B plus.
Right. But so it's intuitively this operation has a boundary. If this were, because I have to put the base point here, so, and it's intuitively, I mean, it's sort of, there's a pictorial idea behind this equation. So this gives the proof that I want that it's homotopy commutative. It's another operation on loops of degree 1 more than the previous one. By the way, if you want to have things graded in a convenient way, you can shift the grading over by D, and that will make the grading now behave the usual way. Then this will be +1. I'm going to say that anon. Okay. So now notice that we take this operation and skew symmetrize it, then this will commute with the boundary because it's like this star operation is like a path between A times B and B times A, and this is like the other path, and so the two paths taken together form a cycle. And the first idea that a multiplication would be homotopy commutative to the second order would be that you could find a path like this so that when you symmetrize the path, this loop could be filled in by homotopy. And alas, it's not true here. This is there's a hole here in this path, and this cycle defines a new operation of degree minus D plus 1, namely I and J go to I plus J minus D plus 1, and this commutes with the boundary operator because, it's the picture. And this defines operation bracket, which will pass to the homology. So it's sort of the residue of non-commutativity at the deeper chain level that you get out of the chain. This is the good reason why you'd like to. You don't really ever, in my world, I never pass the homology. I stay at the chain level because there's always this additional structure that might be there, and you have to. You sort of pass the homology to look at things, and then you go back to the chain level when you go to sleep at night. So here's the theorem 1. So now I'm doing this shift. So let's take the homology of the free loop space, L, of a manifold, MD, shifted to the left by D, so that what was in degree D is now in degree 0. I never know how to write that with this notation if I can save it. So this is a graded commutative associative algebra dot with a compatible Lie bracket. This bracket satisfies the Jacobi identity and is compatible with the multiplication in that the Leibniz rule is true. So this is theorem 1. It says that the homology of the free loop space with this very simple algebraic structure and with this derived operation coming out of the natural homotopy, making it homotopy commutative, has the structure of an algebra with two operations, a multiplication and a Lie bracket, which are compatible. These things have a name. They're called Gerstenhaber algebras. But so on. What? No, because of the +1. That's all. If it were 0, if the bracket had the same degree, it would be called a Poisson algebra. Yeah. Okay, so that's the theorem then that the free loop space of a manifold, the homology has the structure of a commutative associative algebra with a compatible bracket, and this thing exists at the chain level. Let's see. How much time do I have left?
20 minutes?
20 minutes? Okay. Okay, now, there's another very familiar operation in this space of loops, which I'm mapping. Maybe I'm taking all maps of the circle into my manifold. That's my space. I'm script L, right? So I've shown its homology has these two operations, which are not part of the usual operations of algebraic topology. They really are using the idea of using the geometry of the picture of what this space means, a cell of loops, and doing something in the finite dimensional manifold. So now there's another operator which we have to put in mind, is that there's a symmetry, like there's a gauge group in this problem, rotating the circle. You can rotate the domain of the mapping. And there's a natural circle action on the free loop space. So if you have any chain, you can roll it around by the circle action and get a chain of one higher dimension. So there's a lift operator. I think I saw you do this in a talk. So I'm doing it now. And I call it lift. Maybe did you call it lift too? I don't know. Doesn't matter. I don't know why I started calling this thing lift. Anyway, so there's another. So this has degree +1 by rotating the base point. Now, theorem 2 is about a. Sorry, let me do this thing that I always hate when other people do it to me. But. All right, so on the homology, so L is this operation on the chain level. L squared is not 0 in homology, but when you go to the, sorry, L squared isn't 0 at the chain level, but it is 0 in homology, because if you run the base point around once and you run it around twice, there's kind of a torus there which is degenerately sitting on a circle, so it's homologously trivial. Anyway, so L, there's another operator, a unary operation on the homology of L. It satisfies L squared is 0. L squared is not a derivation of our product, which is what you would try first. But the deviation from being a derivation is L of AB minus A L of B minus L of AB is in fact equal to this bracket. So this Gerstenhaber bracket is actually the derived entity from a unary operation, which is not a derivation. So, in fact, we didn't really need to introduce the bracket. We could have just said, hey, here's this multiplication. Very simple to define. L is already there. And if you form this deviation from being a derivation, you get a binary operation that satisfies Jacobi and compatibility with the multiplication. It follows formally that L is a derivation of this bracket. So L is a derivation of the bracket. It's not a derivation of dot. These algebras have a name which are called Batalin-Vilkovisky algebras. An algebra with this structure. So in fact, we have that. So this, the free loop space has, homology has a structure of a BV algebra, in fact. Okay, now we go to strings. So what's a string? So informally, the string space, S of M, is the space of all loops modulo the action of S1. So in some sense, I want to think of an abstract one-manifold, cells of which are families of abstract one-manifolds, but there's no base point running along. That's what I'm calling a string, closed string. I have a little more detail here. So a cell in my loop space was formally a map of a cell across the circle into M. That's the operational definition of a cell. A cell of strings is the following, a little more abstract, but this is what you can work with. You have a cell or any family, you have a circle bundle over that cell and a map of the total space into M. That's sort of a nice way to say what a family of circles is. So you have a family of abstract circles. You don't have a trivialization. If you, over a contractible space, you can choose a trivialization and get one of these, but there are many ways of choosing it. You can spin them around. So the abstract thing is that. And over something with topology, you might not be able to choose a trivialization. So anyway, this is a nice working definition of what a family of strings is. Anyway, so it's just intuitively, it's a family of one-manifolds moving along. And now there's a couple of operations that relate these two spaces. Here's a loop, here's a string. Well, we could just erase the marked point and get a loop. That's a degree 0 operation on the chain level. Another thing we could do is we could take a string and we could put the mark in all possible positions. Oh, that's why I call it lift, because you're lifting strings up to loops. And that's a degree +1 operation. If you erase the mark and put all possible marks, that's the operation L that I talked about before. And if you'd go the other way, it turns out you get something which is homologous to 0. But now we can take our algebraic structure up here and project it down here using these maps and see what we get. And that's actually where we started with more on this. So we make an operation on strings like this. We take two families of strings, we mark them, so we put all possible marks, we intersect them, and then we erase the mark. This defines a binary operation on families of strings. And theorem 2 is, on the chains of string space, this bracket operation satisfies Jacobi up to infinite homotopies. And the homology of S, and it's obviously compatible with the boundary. Everything here is compatible with the boundary. The boundary of is defined on the chain level, and boundary of the product is the Leibniz rule. And so the homology of F of the string space of a manifold becomes a graded Lie algebra. And the degree of this operation is minus d plus 2. That's your 2. And the I thing and a j thing goes to I plus j minus d plus 2 because of the two m's. Okay? And to be honest with you about the signs, if the manifold's even dimensional, the parity is what you expect. And if the manifold's odd dimension, you have to change the parity to make the homology into a graded Lie algebra. The parity that you use is either the same, the one you had before, or shifted if the manifold is odd dimensional. Okay, now, so this is, it gets back to the title. I claim what this is a mathematician's topologist way of trying to say what this basic string interaction is, namely where you have two strings, they come together, they touch, and then they break apart and become one string. This is exactly a concrete construction that goes with that picture. And so there's a paper of Witten where he discusses this interaction and he observes that it's not associative, and just on some formal level. But it's not associative because it satisfies Jacobi in this context. Now, this wonderful thing is not due to me. This is just my attempt to understand what wonderful thing somebody else did. So here's the wonderful thing somebody else did. And this connects to a lot of the talks that have happened in this conference. Let's take the space to be a surface. And let's look at the strings on the surface. And let's just look at H0. I mean, so what that means is just the surface has a lot of fundamental group, and there's a lot of different homotopy classes. So you have a lot of components, and H0 is just linear combinations of the components of the homotopy classes of maps. So it's a big infinite dimensional vector space. And remember, the formula is I plus j minus d plus 2. So when d is 2, you get I plus j. So when I and j are both 0, you get 0. So this bracket induces a Lie algebra structure on this infinite dimensional vector space. And this is the bracket arising in the work of Thurston, Wolpert on Teichmuller space, and Goldman on the symplectic nature of the space of flat connections on surfaces. And here's a nice picture of the Goldman brackets. This is called the Goldman bracket. We take two components of this free loop space, which are just two curves on the manifold, and then we mark them by letting our base point be anywhere, and then we look at where they intersect. And then at each point of intersection, we go around the black curve and then around the green curve. And then it's a 0 chain, so we just add them up. And this amazingly satisfies the Jacobi identity. You can go home. It's amazingly that it's well defined. Oh, there's a sign here because you put this product, and this is not just a point, it's a point with an orientation. It's a 0 cycle. So there's a sign. We can just think of that as a sign, though, because a point has a canonical orientation. So you put the sign here, which is the intersection number of these two oriented curves. And this operation on curves on a surface is well defined. That's the first miracle. And secondly, it's skew symmetric. And thirdly, it satisfies Jacobi identity. And I heard about this in '85, and I thought it was wonderful, but I didn't know why, because it was couched in all this language of symplectic geometry and stuff. Anyway, this bracket is the same as the bracket on functions coming from the associated symplectic structure, where the function is given by, for example, on Teichmuller space, the length of the closed curve we're talking about, or the trace of the holonomial of the flat connection. And that's a function, and then you have some bracket. And this operation is compatible with those structures. So this Lie algebra structure is sort of defined on the free loop space, string space of all manifolds, and it's somehow, down in this case, it's perhaps quite interesting. And it fits with some of these things that we've heard about. Let's see, I've got 8 minutes now. 10? Okay. All right, well, okay. So this is a bit of the tip of the iceberg, though, in this story, because once you have this idea of letting things come together, you can now, there are a lot of string operations. So that it's like you send your child to summer camp, and you might be, you go in one day and you might be doing the following thing, taking a bunch of the necklaces and cutting them open into a bunch of shorter interval pieces, and then in some random way re-gluing them back together to get some circles. So this is what I call a naive string operation. You take a bunch of strings and you just cut them apart into a bunch of intervals and then re-glue the intervals in some way. Now you can stick this into the previous discussion. You just, when you want to do the gluing, you have to lose d dimensions in your families to make these, if you want to glue this point to this point, you have to intersect these points the way I did before. But then you do that, you cut down as many dimensions as you have to, and you put them all together, glue them up.
You glue them, they all come together.
Oh, well, the combinatorial data for this has to be specified. You have to give cyclic orders, and it's a whole nother. I just wanted to indicate that there's a lot more things. Already, this picture is a good indication of, this would be where n strings give one string. So you sort of think of them fusing together like this, and you get an operation with so many parameters. And at the chain level, when we learn to work at the chain level, we actually have to think of these operations with the right number of parameters. And we could, for example, let this, like the star operator, we let the attaching point moved around. Remember, we gave ourselves a 1. We could put in these other parameters. We have cells of operations. So we have a whole complicated set of chain mappings. And when we just do this n1 thing, they're kind of organized by the configuration of n points in a disk with marked points. And so actually at the chain level, you have n to 1 operations that are organized by the cells of this configuration space where these are labeled. And there's this beautiful theorem of Cohen and Gessler that the homology of this is exactly the universal operations in a BV algebra. So the explanation for theorem 1 is that at the chain level we have the universal thing for BV algebra, but I don't want to talk about that in any more detail. Let's see, so that's the structure of the last part is that so I made a kind of coherent discussion of the single interaction and the interaction with L, and then going down to string space, you get a bracket. And then I've indicated that there are many more operations and which need to be studied.
To understand correctly, each particular operation is essentially constructible from what you said.
Yes, not essentially, but you have to specify an interval of attaching, not just a whole circle. So given that interval, you're right. That's right.
So structured.
Right, but what I claim to be able to do is to give a linear basis for all the operations. So see, if you just take generators, you start composing them, you don't know what the vector spaces you get. I want to describe a linear basis for the operations and then write an expansion of a composition out in terms of the basis. Anyway, so we're just doing intersection theory on the cells of the loop space, and so this picture is supposed to kind of explain why you got this. I mean, it's kind of a sophisticated explanation. You have to know some things, but just this picture explains why we got a BV algebra before. I mean, this is why God knows it's a BV algebra, because this is the universal algebraic structure behind the BV algebra. But there's a lot more use in here, just like in homotopy theory, the cohomology structure, you have higher order products and this derived bracket from the non-commutativity. There's a lot more structure in the statement that you have this at the chain level than the theorem I mentioned, although that is like technical and professional statement. Now these operations include co-operations. I mean, I didn't start talking about those, but just if you take the diagram where you're going to let a single string go along, come close to itself, and then hit itself, and then break apart into two strings. That'll be an operation. That'll be an operation on the cells into the tensor product. And you have to do this with an equivariant transversality argument, and there's a technical problem, and it's better to pass to immersed curves. So we can replace the space of strings by immersed strings, and a topologist can calculate that just as easily because of the Smale-Hurst immersion theorem. You know how to calculate that space as well as the first one, so that's no problem. And that's another thing I wanted to say, that all these operations respect auxiliary conditions. So if you wanted to work with immersions, these operations respect immersions. If you wanted to work with curves transversal to something, they respect that too. So this is actually a kind of methodology rather than just examples as I've presented it. So you can work in these immersed curves, and then this operation here defines a coproduct. It satisfies co-Jacobi, and it with the previous bracket. So the two basic operations of strings combining or strings splitting apart are operations that fit together to make the homology of the space of immersed strings into a Lie bialgebra. So you have Jacobi, co-Jacobi, and compatibility between the two operators. The one acts kind of as a derivation of the other. And even for R3, we checked in the restaurant last night that this is non-trivial. Because even though the space is contractible, the space of immersed curves is not. It has a little juice in it. It's got the Betti numbers of the space of strings in R3 are 1 in every dimension. And this operation is non-zero there.
But when you multiply immersed string, you have to have some canonical operation of smoothing of this intersection.
Not much. No, because the intersection, yeah, I mean, it's transversal intersections. You just go around the smooth corner. You know, when you drive your car around a corner, you sort of...
Yes, but it's in big family, so it should be kind of very canonical.
No, but this doesn't matter because, again, the nice thing about this algebraic topology is that it's very robust. You just have to have things approximately up to small errors and have it be well-defined up to contractible choices. And then you get a well-defined with identities holding up to infinite homotopy and so on. So it's sort of good to get that viewpoint, socked into you first, and then you can go as if they're true equations. Because the idea is it doesn't matter the details of how you break these spaces up into cells. Any two choices will be quasi-isomorphic. There's an intrinsic structure which is there, which we're talking about, which is easiest to describe in homology, but it's actually behind homology at the chain level. And so this is the final theorem that I wanted to mention today, that we have this Lie bialgebra. And this, again, is not my invention at all. Turayev in '88 looked at Goldman's thing and noticed this operation on surfaces and noticed it was a Lie bialgebra. And this is due to him for surfaces, for H-0 surfaces. And this is such a beautiful thing. I thought you should try to understand what it means. And so it's part of this bigger discussion about loop space. Here's a challenge to the audience that the bracket structure here is related to the symplectic structure of gauge theory by the Poisson bracket of functions. A curve determines an observable and some symplectic thing, and you have the Poisson bracket, and this bracket is compatible with that. But apparently there's no interpretation in the symplectic world and quantum world at the same level for this co-bracket structure. So this Lie bialgebra structure is just sitting there waiting to be...
How did Turayev introduce it?
He did it just by geometry. Yeah, in other words, you just take the same picture on surfaces, and self-intersection is a little more subtle. It's not take two copies and intersect, because that would give, when you take two copies of something and intersect, you get that picture, right? You get 2 points, but it's the self-intersections. You have to do things equivariantly, and that's why we need this immersion. But there's another way around it too. So anyway, so I guess the conclusion is the space of strings in a D manifold has a Lie bialgebra structure in its chains that pass it to homology. And this is part of a lot of other naive string operations. That's all. Thank you very much.